This video is about thermal energy or heat energy, another type of energy. Thermal energy is the energy associated with heat and temperature. Thermal energy appears as a result of friction, air resistance, impacts, and other interactions between objects. Thermal energy is actually a measurement of the random kinetic energy of vibrating particles in an object. We're going to talk about this more in a future unit. For now, I just need you to know that what thermal energy is, what our experience of temperature and heat actually is really just the random vibrations of atoms and molecules in a substance. There's nothing else to it. The variable for thermal energy is a little strange. It's capital E subscript INT. This means internal energy. The reason it's called this is because this is the internal kinetic energy that an object has because of all the random movement of the particles inside of it, if that makes sense. So even if the object isn't moving, the particles internal to it might still be moving back and forth, and so it has some internal thermal energy. The unit for thermal energy is, again, J for joule, because all energy is measured in joules, and again, it's just the ability to do work. As a general rule, thermal energy is almost always calculated by finding how much energy has been lost from an object or system. Energy is never truly lost because it can't be created or destroyed, but if it's turned into thermal energy, that usually means that we can't use it again, just because thermal energy is more difficult to capture and use than other types of energy. Here are a few examples of transforming energy into thermal energy. Friction transforms kinetic energy into thermal energy, so if an object is moving along the ground and it encounters friction, it's going to have less kinetic energy than before. And what's happening there is that the amount of kinetic energy that it lost was transformed into heat energy. And that heat energy can stay in the object, it can go into the floor, it can go into the environment around it. Thermal energy has a tendency to spread out like that. I'm using thermal energy and heat energy interchangeably here. I should probably just stick to thermal energy. We can calculate the specific amount of thermal energy that's created using friction, because friction creates thermal energy. So as an example, if this frictional surface is 5 meters long and it applies a 10 Newton force of friction back on this object, I know that the work done by friction is equal to negative 50, 10 newtons times 5 meters, and the two things are pointing in opposite directions, so the work is negative. And so if the friction is doing negative work, what that means is that it's taking energy out of the object. It's taking exactly 50 joules out of the object. So that means that the exact amount of kinetic energy lost to thermal energy is exactly equal to the work done by friction, which is 50 joules. So if this object was moving with a certain amount of kinetic energy, it just lost 50 joules of that kinetic energy to thermal energy. We can also calculate the total thermal energy created if we know the kinetic energy before and after. Like if before we find that this object had 200 joules of kinetic energy, and after it only had 150 joules of kinetic energy, we know that the internal energy, the thermal energy created in that interaction is 50 because it lost 50 joules of energy. When an inelastic collision occurs, when two objects stick together, some kinetic energy is lost to thermal energy. Sometimes it's all of the kinetic energy. For example, when a ball falls on the ground and stops moving, all of its energy is transformed into thermal energy. Some of it may be lost to sound energy, like when you drop a ball, you normally hear it hit the ground. So some of its energy was transformed into sound, but most of the energy lost during a collision like that, where an object stops moving due to a larger object, most of that energy is actually going into heat energy. The only other place it can go is really sound energy, and sometimes light energy. When you have an inelastic collision and two objects stop moving, all or some of their kinetic energy is also transformed into thermal energy, and the energy stays in the objects and also moves into the air around them. Just as an example of using numbers for this first one, some problems might ask you how much heat energy is created when a ball falls to the ground. So if you're given the mass and height of the ball, like if the ball is 5 kilograms and it's 5 meters above the ground, you can calculate that the gravitational potential of the ball is 245 joules. And right before it hits the ground, all of that potential energy has been changed into 245 joules of kinetic energy. And then when it hits the ground, all of that energy is dissipated as heat energy. So it loses 245 joules of energy to heat to the environment around it. We're going to be talking about collisions a lot more later on in this unit, so I'm going to hold off on talking about specific equations for inelastic collisions right now. Just one thing I need you to know is that in a perfectly elastic collision, no kinetic energy is lost to thermal energy or sound energy. This is actually the technical definition of an elastic collision. A perfectly elastic collision is one where not only is the total momentum conserved, but the total kinetic energy also remains exactly the same and no energy is lost to heat or sound. So that's what you need to know about thermal energy. We're going to be working with this idea a lot in this unit and in the future.